Now we're going to talk about another method of integration in this chapter called partial fractions. And if you see the guidelines up at the top of the notes here, partial fractions it's typically used to integrate rational functions. So the steps are use long division to divide improper fractions so that the degree of the numerator is strictly less than the degree of the denominator, because you want the degree of the numerator to be strictly less than the denominator. Factor the denominator completely into linear and quadratic factors. So if you have a polynomial in the denominator, it's x to the 6 is 6-degree polynomial, you have to factor all the way down to linears to powers and quadratics to powers. And then you do what's called the partial fractions decomposition. So you rewrite the integrand in another way. So the whole idea is of partial fractions that you have a rational function you don't know how to integrate. So we're going to rewrite the integrand in a different way into smaller pieces that you can integrate, hopefully. So we talked about how to do the decomposition last time. So let's just get into the first example. So it's the integral of 5x squared minus 12x minus 12 divided by x cubed minus 4x. Okay, now again, just because it's a rational function doesn't mean you jump to the partial fractions method, okay? You should run through the methods. Is it a straight integration problem? No, I don't know what to do there. What about a substitution? Well, the common thing that you did in Calc 1 when you had a rational function with the degree of the numerator strictly less than the degree of the denominator, you let u be the denominator, So if u is x cubed minus 4x, du is 3x squared minus 4, and that's not looking real promising, okay? And again, why not integration by parts? Well, parts is typically with products, so you'd have to think of this as 5x squared minus 12x minus 12 times 1 over x cubed minus 4x. That's not looking promising as well. Okay, so let's try partial fractions. All right, so the degree of the numerator is strictly less than denominator, so that step is taken care of. Step 2 said factor the denominator completely into linear and quadratic terms. Okay, so, well, first step in factoring is always pull out greatest common factor. So if you factor on an x, you're left with x times x squared minus 4. But that's a difference of squares, and so that factors as x plus 2x minus 2. So I've gone ahead and I've written the factorization there. Okay, so we have satisfied, we've rewritten the integrand. And no, I didn't write integral sign because we have to do some algebra here. Okay, notice I have x, x plus 2, x minus 2. Linear term, linear term, linear term. Okay? So based upon what we talked about last time, how do we rewrite this rational function and do the partial fractions decomposition? Well, we have x to the first, okay? So we have to start with this term, right? It's just over x. Now, what if that had been x cubed? That would have been linear x to the third power. We'd have to have x, another term with x squared, another term with x cubed. You have to count your way up to the highest power that's on it. But it's a first power, so you start with 1 and stop with 1. Notice this is also a linear term to the first power. So we also need a term for this one, x plus 2 to the first, so we just have x plus 2. Again, what if this had been x plus 2 to the fourth? We would have to have an x plus 2, x plus 2 squared, x plus 2 cubed, x plus 2 to the fourth. And same, x minus 2 to the first, so we need a term with x minus 2. Okay? And remember, when you have a linear to a power, the numerators are all constant, so I'll just write a and b and c for the constants, okay? So the idea is, how do we rewrite this function to make it look like this? So we have to find the constants a, b, and c such that these two functions are the same function. Now, something that's a little helpful here, let's get rid of the rational part. Let's multiply both sides of this equation here by x times x plus 2 times x minus 2. Okay? So if I multiply, and notice that is the least common multiple of all the denominators over there. So if I multiply by x plus 2x minus 2 on the left, I just get 5x squared minus 12x minus 12. If I multiply x plus 2x minus 2 on the right, in the first term the x cancels, I get a times x plus 2x minus 2. When I multiply by the b term here, the x plus 2's cancel, I get b times x plus 2. And when I multiply by the c term, the x minus 2's cancel, I get cx times x plus 2. This should have been a minus. Right, so So when I multiply this times the b term, the x plus 2's cancel, I get x times x minus 2. Okay, so notice I have a polynomial on the left and a polynomial on the right. Now there are two ways to solve for a, b, and c. I'm going to show you one way here, and I think in another example I can show you the other way. You can't just necessarily do it the way I'm going to do it here because it doesn't always work. That's why I'm going to show you another way. Okay, now we're thinking of this as a polynomial function and this as a polynomial function, which means whenever you have two functions, if I had f of x is g of x, what does it mean for two functions to be equal? No matter what I plug into this function, like if I take f of 7, if I plug 7 into this function, you have to get the same answers for y. Okay, so that's the fact I'm using here. If this polynomial, if I think of this as a polynomial function, and this is a polynomial function, no matter what I plug in for x on this side, I have to get the same value over here. Now, just to make things easier, I mean, you can plug in any number you want for x. I could put x equals 17. Plug 17, 17, 17, 17, 17, 17, right? But you're going to get, a number is a number times a number times b, a number times c. To make our lives a little bit easier, it would make sense to eliminate some of the variables, right, to make the algebra easier. In particular, for example, what if I let x be 0? If I let x be 0, you'll have b times 0 times negative 2. That term is gone. And I plug in a 0 there, that term is gone. So I'll just have a. Okay? So again, you should tell me what you're doing here. So for x equals 0, I'm plugging in 0 on the left and 0 on the right. So when I plug in 0 on the left, you get 0 minus 12. I get negative 12. And if I plug 0 on the right, again, this term and this term are gone. So I'm only left with this term. And when x is 0, I get 2 times negative 2. I get negative 4a. So if you choose the right numbers and eliminate some of the variables, the algebra turns out to be a lot easier. So notice I get a is 3. Okay? Again, you can pick any number you want to plug in for x, but if I plugged in x to 17, I would have gotten a number is a number times a number times b, a number times c. You couldn't have said a is whatever. So it helps to eliminate. So now I have a is 3. Okay, so let's choose another value for x. Notice when I plugged in x as 0, I got rid of these two terms. What's another reasonable value to plug in? What if I plug in x as 2? Then these two terms will disappear. So for x equals 2, on the left-hand side, what do I get? Let me see, that's 4 times 5 is 20. Minus 24 is negative 4. Minus 12 is negative 16. Let me check myself. That's 4, that's 20, minus 12 is 8, minus 24 is minus 16, right. When I plug 2 in the right-hand side, this term is 0, that's gone. This term is 0, that's gone. And I'm plugging in 2 down there. 2 plus 2 is 4 times 2 is 8, I get 8c. Right, so again, we eliminated the a and the b and made things a whole lot easier, and so c is negative 2. Okay, not bad. So all we have to do is find b. So it'd be nice to eliminate a and c, and notice to eliminate those, you let x be negative 2. So for x equals negative 2, if I plug negative 2 on the left-hand side, that's 20 plus 24 is 44, minus 12 is 32. Let me check that. Negative 2 squared is 4 times 5 is 20, plus 24 is 44, minus 12 is 32, okay? Now when I plug negative 2 on the right-hand side, that's 0, and that's 0. So I'm just left with this term. Again, x is negative 2 minus 2, so that's negative 4 times negative 2 is 8, and I have 8b, and b is 4. So I solve for a and b and c. So suppose you hadn't done it this way and you plugged in x is 17, and you plugged x is 13, and you plugged x is negative 12. You would have gotten a number is something a, something b, something c. That'd been one equation. Another equation, you would have gotten a number is something a, something b, something c, and then a third one of the same form. So you'd have 3 equations and 3 variables. You could use elimination or substitution to solve which would be a lot more work. So it's much easier if you can eliminate two of the variables simultaneously, and makes your life a whole lot easier. Okay, so a is 3, b is 4, c is -2. So let me go back to the original problem. Right? So this function right here, this rational function, is equal to this, where a is 3, b is 4, and c is -2. So let me rewrite it. So a is 3, so this is 3 over x. B is 4, plus 4 over x plus 2. And c is -2, so -2 over x minus 2 dx. So I just replace this function with its partial fractions decomposition with the numbers plugged in. Okay, so this function's the same as that function. So now I don't need any of this. I've rewritten all that work was just to rewrite this function another way. Now the goal is, can we integrate our new, well, it's the same function written in a new way. So can we integrate now? Well, yeah, no problem, right? We know the integral of 3 over x. Think of that as 3 times 1 over x. That's 3 natural log absolute value of x. Okay. Now, what about 4 over x plus 2? This is a linear substitution, right? If u is x plus 2, it's a 4 over u. It's another natural log, right? And notice the slope is 1, so you don't have to adjust for the slope. 1 over 1 is 1. So this is plus 4 natural log absolute value of x plus 2. And same thing down here. If you let u be x minus 2, it's a linear substitution with slope 1. Again, it's a minus 2 over u. So it's minus 2 natural log absolute value of x minus 2. Don't forget your plus c, because it's an indefinite integer. So all the work here was just to do the partial fractions decomposition. The integration itself was very easy. Okay, let's do another example. Okay, so this integral is 4x squared over x cubed plus x squared minus x minus 1 dx. Okay, so again, you should convince yourself it's not a straight integration problem. You should convince yourself it's just not a straightforward substitution problem. Again, integration by parts doesn't look very promising. It's certainly not a trigonometric integral. Okay, all right, so I say, oh, it's a rational function. Let's try parts. The degree of the numerator is strictly less than the degree of the denominator, so that's no problem. So we just need to factor the denominator. So I'll just do this over here. So we have an x cubed plus x squared minus x minus 1. Because there are 4 terms, the strategy I usually use with 4 or more terms is factoring by grouping. So remember how that goes. Just group 2, put 2 of them together and 2 of them together. You pull out the greatest common factor, okay, of the first one. So let me factor out an x squared out of the first 2 terms. So that's going to be an x plus 1. And then the goal is to factor something out of the last 2 terms so that you also get an x plus 1. So, I mean, I can't just leave that alone. To get an x plus 1, I have to factor out a -1. And then you'll get x plus 1. Right? Check your factoring by multiplying. X cubed plus x squared minus x minus 1. Okay? Now, the reason why you want the same thing, I have the same thing here and here, so I can factor that out of both terms. So if I factor x plus 1 out of this term, I'm left with x squared. And if I factor x plus 1 out of this term, I'm left with minus 1. And again, you could check by factor. That's x cubed minus x plus x squared minus 1. That's exactly what it is. Okay, so that's what our denominator turns out to be. 4x squared over, oh well, okay, let me be careful. That's a difference of squares. I can factor that too. That's x plus 1, x minus 1. Okay, so now notice what I have in the denominator. I have an x plus 1 squared times x minus 1. Okay, so the degree of the numerator was strictly less than the denominator, and I factored the denominator completely. Okay, so that takes care of that. Now we have to do the decomposition. Now I know that x plus 1 squared is a quadratic, but it's not irreducible. Okay, remember it's already factored completely. Don't think of this as a quadratic. This is a linear to a power. Okay, so when we in the decomposition, when it says factor in terms of linears and quadratics, I mean a quadratic, something x squared plus something x plus c that you can't factor. That's what they mean. So this is a linear to a power and a linear to a power. Okay, so how's the decomposition going to go? So I'm just writing the integrand. Now how are we going to do the decomposition? This is linear to a power, so we have to count our way up to second power. So the first I need x plus 1 to the first power, and then you need another term with x plus 1 squared. Because that's a square. If this had been a cubed, I would have had another one with x plus 1 cubed, right? You start with that to the first power and count up until you get to that power. This is x minus 1 linear to the first power, so we just have to have x minus 1 to the first. So this term is just like the last example we did. It's only to the first, so you just have that. Since this is square, you have to have that to the first, that square. Now, this is linear to a power and a linear. Okay? I know there's a square here, but don't think of that as a quadratic. Because it's linear to a power and linear to a power, all of these expressions have a constant in the numerator. Okay? Linear to a power, linear to a power. So because of that, you have constant, constant, constant. And now we're back to sort of where we were before. Okay? Let me show you another. Well, okay, first let's get rid of the fractions. So I'm multiplying through by x plus 1 squared, x minus 1. If I multiply the left side by that, I get a 4x squared. If I multiply x plus 1 squared, x minus 1 times the first term, one of the x plus 1's cancel, I get a times x plus 1, x minus 1. If I multiply the denominator times the second term, the x plus 1 squareds cancel, I get b times x minus 1. And if I multiply that times the third term, the x minus 1's cancel, I get c times x plus 1 squared. Right, so when I multiply that, I lose one of those. Multiply by that, I lose that. Okay, and I multiply by that. Okay. Now, could we do the same game that we did on the last example? So, for example, if I let x be 1, these two disappear, and you'll be able to find c. If I let x be negative 1, these two disappear, and I could find b. Notice, I didn't find a. Okay? So what could you do then? Just pick any number you want. 1. Well, we already did 1. 2. Plug it here, 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 and here. You would know b and c at that point, so you could put b and c in their place, and then you could solve for a. Okay? So keep in mind, if things don't drop out, right, do the ones you can. Like I said, plug in 1 and minus 1, you can get b and c. But then you're not going to get a that way, okay? So that's going to be a problem. So again, what do? Just pick another value for x, plug it in here, 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 and here. You would know b and c, plug those in as well, then you could solve for a. So you could do that. But I want to show you another way to think about this. Because sometimes you can't get rid of stuff, okay, if they're irreducible quadratics. So let me show you another way to think about this. Let me rewrite the right-hand side the way we would write a polynomial, something x squared plus something x plus a constant. So let me work that out here. Oops. So this is a times x squared minus 1. I just multiply those together. Plus, plus b times x minus 1 plus c times, if I multiply that out, that's x squared plus 2x plus 1. Okay, I'll go ahead and write it out. So you get ax squared minus a plus bx minus b plus cx squared plus 2cx plus c. So I just distributed the a, the b, and the c. Ax squared minus a, bx minus b, cx squared plus 2cx plus c. Okay, so I want to rearrange and put the terms together. Let me come up here. So I get 4x squared. Now where are the x squared terms? I've got ax squared and a cx squared. So that's a plus c x squared. See what I'm doing? I'm writing this as something x squared plus something x plus constant. Now where are the x terms? I have a bx and a 2cx. So that's plus b plus 2cx. And then where are my constants? I have a minus a minus b, and a plus c. So I'll just write that as c minus a minus b. I just wrote the c first because it has a positive in front. All right, so let me check myself. That's ax squared plus cx squared, ax squared plus cx squared, bx plus 2cx, bx plus 2cx, plus c minus a minus b. So notice it's 1, 2, 3, 4, 5, 6, 7 terms, 1, 2, 3, 4, 5, 6, 7. I didn't leave anything out. Okay, so I don't need this anymore. Okay, so a fact that you probably learned a long time ago in pre-calc, if you have a polynomial function equal to another polynomial function, as I mentioned, f of x equals g of x, no matter what you plug in for x, they have to give the same answer. But another fact from that is, if you have one polynomial function is equal to another polynomial function, the only way that can work is if the degrees are the same, so the highest powers are the same, and the corresponding coefficients are the same. My point is, if I had a function, f of x is x cubed plus x squared plus 7, and I had another function, g of x is x to the 4th plus 4x squared plus 3x minus 1, I know these are not the same function because the degrees aren't the same. Okay, that's the fact I was just mentioning. Okay, what if I change this to a cubed? Okay, so the degrees match, but could these be the same function? No, because those coefficients match, but the coefficient of x squared here is 4 and the coefficient's 1. They're not the same function. Okay? Okay, so that's the fact I'm using here. So I have 4x squared is equal to this. Well, what would have to be true? 4, the coefficient of x squared here, has to be the coefficient of x squared here. So I know a plus c has to be 4 for these to be equal. Notice b plus 2c is a coefficient of x. The coefficient of x on the left-hand side is 0. So b plus 2c has to be 0. And the constant term here is c minus a minus b. The constant term on the left is 0. So c minus a minus b has to be 0. Okay? So again, this is just another way you can approach these. I mean, the way I mentioned before when I had the polynomial here, plugging in numbers and eliminating terms, that's perfectly fine. But I want to show you this other method in case that doesn't get you anywhere. Okay, so you have a choice. So we could have done this method on the first problem too. Okay, the right-hand side as a polynomial, something x squared, something x constant, set all the coefficients equal to each other and then solve. So this is going to take a little bit of work. Notice the way I mentioned before, plugging in the 1 and the minus 1 to get b and c, and then plugging in something else to get a is easier than this. But I wanted to show you this method. So what can we do here? Let me just solve for a. I'll solve for a here. So a is 4 minus c. A is 4 minus c. So there's no a here. Let me plug 4 minus c in for a here. So you'll get c minus 4 minus c minus b is 0. So I'm replacing a with 4 minus c. Notice there's a negative out front. So if I simplify, I get c minus 4 plus c. So I get 2c minus 4 minus b is 0. Or let me rearrange terms here. Negative b plus 2c is 4. All right, let me check myself. So 4 minus c goes in for a. That gives me this. If I distribute the negative sign, you'll get c plus c is 2c minus 4 minus b is 0. I wrote the negative b first, then 2c, and I took 4 to the other side. Now, why did I do that? Because now I have this equation with b and c, I have that equation with b and c, so I can use elimination. Right. So I'm using this equation that I got from the third one, and then I'm recopying that. So remember, with elimination, the goal is to have two coefficients that match, but they're off by a minus sign, so plus or minus 1. So if I add, if that equals that and that equals that, that plus that is that plus that. So if you add, I'll get 4c is 4 and c is 1. Again, this is a lot longer than the way I mentioned that we could have done this, but I want to show you that this is another way. And so if we go back to this equation right here, c is 1. So b plus 2c, that'd be b plus 2 is 0. b is negative 2. And if c is 1, if I go back to this equation, you get a plus 1 is 4, so a is 3. So that wasn't too bad. Again, this was a lot longer than if I just plugged in x is negative 1, x is 1, and then plugged in another value of x to find the a. But I want to show you this method because sometimes you have to do it this way. Okay, so if we go back to the original problem here, this is going to be equal to the integral of a is 3, so 3 over x plus 1, plus b, well, b is negative 2, let me make that a minus. So b is negative 2, that's minus 2 over x plus 1 squared. And then c is 1, plus 1 over x minus 1. Okay, so we've rewritten the original integrand in terms of its partial fractions decomposition, where I plugged in a is 3, b is negative 2, and c is 1. Now remember, the goal is to hopefully be able to integrate this now. Okay? And we can. Again, there's a linear substitution. U is x plus 1, right? U is x plus 1, so it's 3 over u. So it's 3 natural log absolute value of x plus 1. Let me do the third one because that's easy too. If u is ux minus 1, it's a linear substitution. You have 1 over u. That's natural log absolute value of x minus 1. Easy. So the only one that takes a little bit of work is this middle term. Now notice, if u is x plus 1, that's a linear substitution, right? U is x plus 1. Notice the slope was 1 and 1 and 1, so I don't have to adjust for the slope. But what would that do if I did u is x plus 1? You're going to have the integral of negative 2 over u squared du, which is negative 2u to the minus 2. Again, I'm working it out just on scratch work, because you could do this in your head. And so we add 1 to the exponent and divide by the exponent. If you need to work it out beautifully, you could do that. But it's just a linear substitution. It's just this part you may not be able to do in your head as easily. So notice you get 2 times 1 over u. It's 2 over u. So it's plus 2 over the u, which is x plus 1. Okay, so I sort of worked out the substitution even though it's a linear, but the integral you have to think about a little bit. Okay, so this turns out to be 2 over u, 2 over, and u was x plus 1. So there we go. So again, all the work here, most of the work was with the partial fractions decomposition, not the integration. Okay, let's see what the next one looks like. Okay. Again, notice the instructions say use partial fractions. On a test, I'm not going to tell you what method. This is the integral of x squared plus x plus 3 over. Okay. So again, straight integration, no. Substitution, if you let u be the denominator, no. Because notice if u is the denominator, du is a cubic, and there's no cubic in the numerator. And it's not partial fractions, la la la. Okay, so if we use partial fractions, now we need to factor the denominator. I'm just going to go ahead and do it. It turns out that's x squared plus 3 squared. So that would be x to the 4th plus 6x squared plus 9. So there's factored. Okay, notice you cannot factor x squared plus 3. Okay, so notice we have our first example where we have a quadratic, irreducible quadratic. I can't factor x squared plus 3. I have a quadratic to a power. Okay, so how do we do the partial fractions decomposition here? Okay. So it's just like the linears. You have a quadratic to a power, so you have to count your way up to that power. So I have to have x squared plus 3 to the first, and then I have to have an x squared plus 3 squared. You have to count your way up to 2. So x squared plus 3 to the first, x squared plus 3 squared. If this had been x squared plus 3 cubed, I'd have to have an x squared plus 3 cubed added on to that. Now here's where you have to be careful. When you have a quadratic, irreducible quadratic to a power, the numerator's not a constant. If you don't do the decomposition correctly with things on the top and the bottom, the algebra step, you're not going to get it to work out. You may get a no solution. That's a dead giveaway that you've got a problem. Or you can't solve it because there's an infinite solution, which means you put in too many variables that you didn't need. Okay, so it's very important that you know how to break this down. So remember, when you have a quadratic to a power, the numerators are linear. So ax plus b, cx plus d. Okay. Now don't mess up your problem. I'm gonna just for contrast. What if I had 2x plus 7 as another factor here. Notice that's linear, right? So if I had that extra factor here, I'd have to have a linear term, 2x plus 7. But what would be in the numerator here? Because that's a linear, you just need a constant. Okay, that's what I'm getting at. If you put a linear up here like you did here, you're going to have too many variables, and there's going to be an infinite solution when you're trying to solve, and you're going to run into problems. Okay, if this had been 2x plus 7 squared, I have a 2x plus 7 squared with an f. Again, it's a linear to a power, so you have just f constants. Okay, let me get rid of that. That's not part of the problem. Okay. Okay, so let's multiply both sides of the equation by x squared plus 3 squared. So on the left, I get x squared plus x plus 3. One of the x squared plus 3's cancel, so I get ax plus b times x squared plus 3. And then there, the x squared plus 3 squared cancels, and I get cx plus d. Okay. See here, this is like I was talking about before. You're not going to be able to eliminate x squared plus 3 by plugging in real numbers. Okay. So what I'm going to do here is what I did in the last example. I probably should have waited till this one. Multiply this out and write it as a polynomial. So if I multiply this out, I get ax cubed plus bx squared plus 3ax plus 3b plus cx plus d. Ax cubed, bx squared, 3ax, 3b, cx plus d. Okay, so let's write them in terms of powers. This is the only cube, ax cubed. This is the only square, bx squared. I have an x here and an x here, so that's 3a plus cx. And then my constant term is 3b plus d. X cubed, bx squared. 3a and a c with the x, 3b plus d. Okay. So I have a polynomial equal to another polynomial. So the coefficients have to match. Notice there's a cube term here and there's no cube term here. That tells me a is 0, right? 0x cubed because there's no term. So a has to be 0. A is 0. Notice the only square term is bx squared. That's the only square term here, so b is 1. That's easy. So then we have 3a plus c. The coefficient of x has to be 1. And 3b plus d is the constant term, so that has to be 3. Notice, yeah, we know A, so we can figure out C. We know B, so we can figure out D. So you don't have to do an elimination method like we did in the last problem. So when A is 0, it looks like C is 1. And if B is 1, you'll get 3 plus D is 3, so D is 0. Right? If A is 0, you'll get 0 plus C is 1, so C is 1. If B is 1, you get 3 plus D is 3, so D is 0. Okay, so now let me rewrite my integral here. I don't want to get rid of that. I need to plug in my A's, B's, and C's. So my original problem here turns out the integral of ax plus b. Well, a is 0 and b is 1. So I get 1 over x squared plus 3 plus c is 1 and d is 0. So I just get an x. So it's x over x squared plus 3 squared x. Okay. So I plug in a, b, c, and d into this, my decomposition, and that's what I get. Okay, so now the goal is to integrate that. Let me get something to drink. Okay. Well, how are we supposed to do this? I mean, you might be inclined to try a substitution, but if u is x squared plus 3, du is 2x, and you don't have an x up here, this should remind you this is an arctan. Now again, if you have the formula memorized, the generic formula, you could just use it and write down the answer. I don't have that memorized. I always do a substitution, but not of this form. I have to do some work on it. Now what about this one? On this one, if you let u be x squared plus 3, du is 2x, and there's an x waiting for you. So this is a straightforward substitution problem, and this is going to be an arctan. Now, you normally do not like to mix variables in the same problem, but I'm going to do it anyway. Oh, before I write that. Let me write this as two separate integrals, just to indicate that I'm doing them separately. Okay. So I'm going to do a substitution on this one, separately, and then this I'm going to try to treat as an arctan. So for this one, I'm going to let u be x squared plus 3. Notice it's not a linear substitution. That's why I'm going to work it out. So u is x squared plus 3. So du is 2x dx. I don't have a 2 in the problem, so let me adjust for the 2. 1/2 du is x dx. Okay, let me come up here. Okay. So well, let me go ahead and write the next step for that one, and then I'll come back and we'll work on this one. So out here, so x dx is half du. Right. So the x dx is half du, and then what am I left with? I'm left with 1, right? The x is already gone. This is u squared in the denominator, or u to the minus 2. All right, let me check myself. So the x dx is half du. The x is already gone. I have 1 over u squared, which is u to the minus 2. Okay, that we know we can do. Now let me come back to the arctan. Again, the way I do the arctan, to make it match the formula, I need a 1 here, right? Oh, so that's what I'm going to do here, right? So remember, to get a 1 there, I'm going to factor out a 3. So this is the integral of 1 over 3 times x squared over 3 plus 1. Right, if I distribute it to 3, I get x squared plus 3. Remember, the goal is to get a 1 here. Okay, and then so the next step, again, let me work with this one some more. Let me pull out the third just to get it out of the way. And then remember, let me leave the plus 1 alone. And remember, this x squared over 3, you need to write as whole thing square. Let me make that bigger. So I have the plus 1. You need to write that first expression as a whole thing squared. Notice it's x squared over 3. It's something squared over 3. I need whole thing squared. So how do you write that? That's going to be x over the square root of 3 whole thing squared. Because x squared is x squared, square root of 3 squared is 3. And let me go ahead and integrate this one since it's here. Again, I don't like mixing variables, but the integral of u to the minus 2 is u to the minus 1 over minus 1. And again, if you write plus c, it's not wrong, but I don't need it because the plus c is still built into this one. Okay, we're almost done with this one. Now, let's look at what we have. Okay, notice if I let u, not the same u here, if I let u be x over root 3, think of x over root 3 as 1 over root 3 x. That's a linear substitution. Okay, so I don't really have to work this out, right? If this is u and I do the substitution, you get u squared plus 1. 1 over u squared plus 1, the integral of that is arctan. So I have this 1/3 out front. You have 1 over u squared plus 1 is arctan u, so it's going to be arctan of x over root 3. But then remember, it's a linear substitution. You have to adjust for the slope. The slope is 1 over root 3. You have to take 1 over that. 1 over root 3 is root 3. And now we can simplify this one. We've already integrated this, right? This we hadn't, so I have to integrate. We've already integrated that. So the negative here becomes plus 1/2, and u to the minus 1. That's 1 over 2u. Uh-oh, I forgot what u was. I erased it. What was u? X squared plus 3. And now I have to do my plus c because I've integrated both. Again, I don't like mixing variables. That's exactly why. But it's all right. So you can write that as root 3 over 3. Oh. In my notes, I have a minus sign. in my notes, I have a minus sign here in my notes at the end, which means that needed to be a plus. So you're gonna have to look back because I've erased everything. Maybe I accidentally put a minus here and it was supposed to be a plus. All right, so go back and look at that. Unless I have a mistake in my notes. So in my notes I have a minus here, which means that should have been a plus, which means that should have been a plus. So you need to look back and see, I hate to say. Okay, let's do one more here. Okay, so this number 30, it says the integral of e to the x over e to the 2x plus 1 e to the x minus 1 dx. And again, go through your list. Straight integration, no. They say use substitution, but just as a straight substitution problem, you can't get the answer just with a basic substitution. You have to do something else. And again, parts, no, okay. So what I want you to realize here is this is not a rational function. It's not a polynomial divided by a polynomial, okay? But you have a bunch of e to the x's in here, right? And the derivative of e to the x is e to the x, and there's an e to the x waiting for you. So the instruction when they say use substitution, what they want you to do is get rid of all the e to the x's. So let u be e to the x, then du is e to the x dx. There's your e to the x waiting for you. So that's what they mean by use substitution and partial fractions. So they want you to do this first. So if I do the substitution, e to the x dx is du. And notice I'm left with 1 over stuff. Now there's u, right? So that's u minus 1. Now what about this? You're going to have a plus 1. Now what's e to the 2x in terms of e to the x? E to the 2x is e to the x squared. Base to a power, you multiply the powers. So e to the 2x is e to the x squared, so that's u squared. Okay? Right. And notice what we have here is a rational function, polynomial over polynomial. So this is a partial, it turns out to be a partial fractions problem, but it's hard to recognize in its initial form because that's not a rational function. But once you do this substitution, u is e to the x, it turns into a rational function. Okay? So I'm going to get rid of that and we'll continue from here. And again, so now treat this as a new problem, right? I mean, whenever you do a substitution or rearrange or something, you want to just treat it as a new problem. Again, straight integration, no. A substitution, let w be u squared plus 1. dw is 2u. You don't have a u in the numerator. And again, you can eliminate a bunch of other stuff. So we're going to treat this as a partial fractions problem. U squared plus 1. And notice the denominator, it is factored completely. This is a sum of squares. Sums of squares don't factor. Okay, so this is factored completely. Okay, now how do we do the partial fractions decomposition? This is a quadratic, irreducible, you can't factor it. This is a quadratic to a power, so we have to have that quadratic to the first. It's first power, so you don't have to count up, it's just first. This is a linear to a power, it's first power, so we just have the linear. Now let's be careful here. When you have a linear term to a power, what goes in the numerator? A constant. When you have a quadratic to a power, irreducible quadratic, what goes in the numerator? Linear. So I need a linear term here, au plus b. This is linear, so I just need a constant there. So that's my partial fractions decomposition, and now we do our algebra. Okay, so if I multiply both sides by u squared plus 1, u minus 1, I get 1 on this side. Then you get au plus b times u minus 1. Because u squared plus 1's cancel. And then you're going to get here c times u squared plus 1. Because u minus 1's cancel. So you could solve for c quickly. If for u equals 1, if you let u be 1, that drops out and you could get c very quickly. But then you can't get c to drop out. Okay, because what are you going to plug in for u to make that 0? Nothing. So I'm just going to do it with the method of setting polynomials equal to each other. So let me multiply out this side. I get au squared plus bu minus AU minus B plus CU squared plus C. AU squared plus BU minus AU minus B plus CU squared plus C. Okay, so I have two U squared terms. I have A plus C U squared. I have two U terms, that's plus B minus AU. And then my constants are C minus B. Notice it's 2, 4, 6 terms, right? 1, 2, 3, 4, 5, 6 terms. So AU squared, CU squared, BU minus AU, C minus B. Okay. So now we need to equate coefficients. I don't have a U squared term over here, so A plus C is 0. I don't have a U term on the left, so B minus A is 0. And the constant on the left is 1, the constant on the right is C minus B, so C minus B is 1. A plus C is 0, B minus A is 0, C minus B is 1. Okay. Okay, so now we just have to solve. Okay, let me do this one. If I solve for B, B is A. Add A to both sides, B is A. B is A. So notice if I replace A with B here, because B is A, I get B plus C is 0. And notice this equation, I just had B's and C's. Let me switch those. Negative B plus C is 1. So now I have two equations and two variables. Let's solve. So if this equals this and this equals it, that sum is that sum. If I add, I get 2C equals 1, because the B's drop out. So C is 1/2. Well, if C is a half and A plus C is 0, it looks like A is minus 1/2, because A plus C has to be 0, and B is the same thing as A. Okay, so there we go. Okay, so we have to plug in our A, B, and C back into this to write the next step. Okay, I'll just get rid of that. So I'm continuing here. So A and B are both negative 1/2, so I get negative 1/2 U minus 1/2 over U squared plus 1, right? Negative 1/2, negative 1/2. And then plus, well, C is a 1/2, so I get 1/2 over U minus 1. Okay, so that's our partial fractions decomposition, du. And so now we want to integrate this mess. Okay, so what we might want to do first, we have a 1/2 here and a 1/2 here and a 1/2 here. Why don't I factor, just because they're both, let's factor a minus 1/2 all the way out front, just to clean that up a little. So if I factor the minus 1/2 out of this, I get a U plus 1 over U squared plus 1. And if I factor a minus 1/2 out of this, I have to change the sign. So I'll get minus 1 over U minus 1 du. I don't really need all those brackets. Okay, there we go. Right, if I put it back in, that'd be minus 1/2 U minus 1/2 plus 1/2. Okay, so that's all right. Now this we know how to integrate. That one's no problem, right? It's a linear substitution. That's going to be a log again. But what about this one? The logical thing would be to do a substitution. Let W be U squared plus 1. But if W is U squared plus 1, dW is 2U. And what do you do with this plus 1? Well, in section 8.1, they mentioned one thing you could do is split up fractions. The thing is, if you let W be U squared plus 1, dW is 2U, there's a U for you, but the 1's in the way. So what we want to do first is break that up. U over U squared plus 1 over U squared plus 1, and then minus 1 over U minus 1. So I left the last term alone. I broke this fraction up, u over that plus 1 over that. So this, we're okay, we know how to do that. 1 over u squared plus 1, we know how to integrate that, that's the arctan. So the only place to do any work is here. Okay, so just to emphasize, I'm only going to work on that one. Let me break up this integral. So u over u squared plus 1 du minus 1/2 integral 1 over u squared plus 1 du minus 1/2, oh, it's plus 1/2, integral 1 over u minus 1 du. So I'm breaking integral of that, integral of that, integral of that, but I have to keep the negative 1/2 on all of them. So that with that, that with that. The negative 1/2 with the minus there is a plus. Okay, so I don't need this. I don't need this. Okay, so we'll just continue from here. Now again, these we already know the answer to. This is the one where we have to do some work. So let's let w be u squared plus 1. So dw is 2u du. But I don't have a 2 in the problem, so I'm going to just 1/2 dw is u du. Hopefully you can see that. Okay, so I'm going to continue here. So u du is half dw, so I get an extra half out front with the dw. And I'm left with 1 over w, right? I already took care of the u du. This is w, so it's 1 over w. And now we know how to integrate those. This is arctan u. And again, this is a linear substitution. Let w be u minus 1. It's 1 over w, that's a log, and you don't have to adjust for the slope because the slope is 1. So it's natural log absolute value of u minus 1. Oh, I don't really need the plus c because I haven't integrated the first term. But we're almost done. So this is minus 1/4. The integral of 1 over w is natural log absolute value of w. And the rest I'll just recopy. Now I have to put the plus c. Oops, w was u squared plus 1. So w is u squared plus 1. So I'm just getting everything back to u's. So all I did was rewrite w as u squared plus 1. And now we have to go back to x's. What was u? U was e to the x. E to the x squared is e to the 2x. And u was e to the x. And then 1/2 natural log e to the x. Ooh. Again, each step wasn't so bad. But there you go. So that ends the section.